Hi everyone, welcome to my 3-minute presentation. For the 3 minutes, I figured I'd go ahead and put up my poster, since that is roughly the amount of time you have at a conference to be able to convey your key points of your research. So, determining the density of ionic liquid C10MPY TF2N confined in silicon nanopores using small and wide-angle X-ray scattering. So what is an ionic liquid? An ionic liquid is a salt that consists of cations and anions in a liquid phase at room temperature. They contain unique properties such as negligible volatility, they are highly electrochemical, and they have thermal stability. The reason why we study these RTILs is because they have been in a variety of fields such as nanolubrication, supercapacitors, solvents, environmental redemption, and new material synthesis. This project concentrates on the density of the RTIL confined in 2 silica pores, and it is known that the dynamic structure and phase transition temperature of the RTILs are changed once they are in confinement. In my research, we have the RTIL confined in 2 different silica pores, one of them being CPG, controlled pore glass, and the other one is MCM, mobile composition of matter. CPG has a diameter of 8.1 nanometers, while MCM has a diameter of 2.8 nanometers. And the reason we use the silica pores is because of their small pore size distribution and high surface area. The ionic liquid I'm working with is the pyrrolidinium-based cation. It is a 5-membered ring that has both alkyls coming from the same location. The instrument we use is SAX, and it is an analytical technique that measures the intensities of X-rays scattered by a sample as a function of the scattering angle. This gives structural information by measuring the scattered X-ray intensity versus Q, where Q is 4 pi sine theta over wavelength. The ionic liquid and silica mixtures were prepared by adding enough RTIL to fill the silica pores, assuming bulk density. They were heated to 70 degrees Celsius and put in vacuum for 24 hours. On the figure on the right here is just calculations pertaining to the research. The data was reduced, normalized by dividing the sample thickness as well as the silica mass. The data was measured in 2 different sample to detector distances, one being 156 and 1200 millimeters for a period of 30 minutes. Our Q range for the data is 0.01 to 3 inverse angstroms. As we analyze the data, we also noticed how the higher Q range in these new measurements can give access to inter-ion distances. The peaks in the ionic liquid show distances at a higher Q, and we can observe the intermolecular distances in analyzing how the peaks in the data shift in the ionic liquid. What we did is that we analyzed the changes in the silica pore-to-pore correlation peak, and we obtained the estimate of the RTIL density. We concluded that that density is lower in smaller pores. The RTIL density was obtained by comparing the intensity at the peaks of the empty and filled RTIL. The density in CPG was 91% the bulk density, and the density in MCM was 86% the bulk density being the density of the RTIL when it is not confined. With these findings in the future, we want to go ahead and use the scattering invariant to find the fraction of silica and the fraction of ionic liquid in the total volume. This will give the density of the ionic liquid at the nanoscale, and we can be able to go ahead and compare our initial estimates of density. One advantage of this invariant is that it uses the full range, not just the peak of the scattering data. And this is the conclusion to my 3-minute presentation. Thank you so much for listening, and take care.